Welcome back to AI Paper Podcasts. Today we're diving into S1, Simple Test Time Scaling, a paper that's been making waves in the AI community.
Yeah, it's a fascinating read.
It really is, and it comes from a team of researchers at Stanford, the University of Washington, and more. They're exploring this really intriguing concept of, well, how to boost large language model reasoning, not by, the usual route of training it more, but by kind of cleverly controlling how long it thinks during a test.
It's kind of flipping the script on the whole bigger is always better mentality we often see in AI, isn't it?
Exactly. And what's particularly cool is how they achieve this with a surprisingly small data set and a technique they call budget forcing.
Yeah, that's the real hook, right?
Absolutely. So let's unpack their approach, maybe starting with how they built this unique data set.
Okay, so they didn't cut any corners here. They started with a massive collection of nearly 60,000 questions. And these weren't just any questions. These were sourced from, challenging places like math competitions, Olympiads, standardized tests, even Stanford PhD qualifying exams.
Wow, they really went all out.
They did, and to ensure they had the right answers and the correct reasoning paths for each question, they actually used Google's Gemini Flash Thinking API. So we're talking high-quality data right from the get-go.
Okay, so 60,000 questions, that's huge. But then they did something, kind of unexpected. They shrunk it down to just 1,000 samples.
Right. Why?
Yeah, what was the logic there?
So it's all about quality over quantity in this case. They filtered this massive data set down to a core set of 1,000 samples based on 3 key principles: quality, difficulty, and diversity. They wanted to make sure every single question in that final data set was, well, a heavy hitter.
Okay, I'm intrigued. Walk me through how they applied each of those principles.
All right, so first up, quality control. They eliminated any questions that had errors from the API or, formatting issues. Kind of like cleaning up the data to make sure it's pristine.
Makes sense. So garbage in, garbage out, as they say.
Precisely. Then they focused on difficulty. They specifically chose questions that could actually stump even those powerful language models like Qwen 2.5, 32B Instruct. The ones that are supposed to be really good at this stuff. These were the questions that truly required deep reasoning to solve.
So no easy questions allowed. They really wanted to put the model through its paces.
Yeah, they wanted to make it work for it.
Now, what about diversity? How did that factor into their selection process?
They wanted to make sure the data set wasn't biased towards any one field or subject. So they included questions from a variety of domains, math, physics, logic, even law. Think of it as making the data set a well-rounded test of the model's reasoning abilities.
Got it. So they've got this powerful yet compact data set, S1K. Now, how do they actually use it to improve the model's performance? That's where test time scaling and this budget forcing technique comes in, right?
Exactly. The paper, it dives into sequential scaling, where the model's computations kind of build on each other step by step, sort of like a chain of thought. And their innovation, budget forcing, is all about controlling that thinking process. It's actually a pretty simple idea at its core. To limit thinking, they just append an end-of-thinking token, forcing the model to, give its best answer right then and there.
So it's like saying, pencils down to the model. Stop thinking, time to show your work.
Exactly. A very strict time limit.
But they can also push the model to think deeper, right? It's not just about cutting it off abruptly.
Oh, absolutely. They can actually suppress that end of thinking token and even add the word wait, prompting the model to think a bit more. It's almost like giving the model a chance to, double check its work or consider alternative approaches.
Interesting. So they're really playing with different ways to manage the model's thinking time, to squeeze out the best possible performance.
That's a great way to put it.
Now, to measure that performance, they focus on 3 key metrics, right? Control, scaling, and performance.
Yeah, they want to see, how reliably they can adjust the model's thinking time, whether performance improves predictably as they increase that thinking time, and of course, the ultimate goal, how accurate the model's answers are.
So it's all about finding that sweet spot. Not too much thinking, not too little, but just the right amount to strike that balance between speed and accuracy.
Exactly. And what's really cool is that their experiments show that budget forcing is a real winner here. It excels in both control and scaling, allowing them to really fine-tune the model's thinking process for these predictable performance boosts.
Hold on, I'm curious about something. You mentioned that this paper primarily focuses on sequential scaling, but I know there are other approaches to scaling out there, like parallel methods. Did they touch upon those at all?
Oh yeah, they do. They touch on those a bit later in the paper, but their main focus is really on sequential scaling and budget forcing for this one.
Okay, got it. So Before we get into that, let's talk results. How does this model, that's relatively small data set and this simple budget forcing trick, how does it actually stack up against the big boys out there?
Well, it kind of punches above its weight class. I'd say they call their model S132B, and it achieves state-of-the-art performance on several of those, classic reasoning benchmarks.
Impressive.
Yeah, it even surpasses OpenAI's O1 preview model on those really tough competition math questions.
Whoa. Okay, so exceeding performance with a smaller data set and this clever budget forcing technique sounds like a big win for efficiency.
It is. It's pretty remarkable.
Do they give us any concrete examples in the paper of how this budget forcing actually leads to these improvements?
Oh, yeah, they do. In Figure 3, they actually illustrate how budget forcing can help the model kind of self-correct and arrive at the right answer.
Okay, how so?
So they present the model with this question, how many R's are in the word raspberry? And without budget forcing, the model kind of starts breaking down the word letter by letter, but then it gets sidetracked, makes a mistake, and ends up with the wrong answer.
It's like it gets lost in the weeds, overthinking things.
Exactly.
Yeah.
But with budget forcing, they append that weight, prompting the model to kind of pause and reconsider.
Okay.
And that's key.
So it's almost like that moment when you're working on a problem and you realize you've kind of gone down the wrong path. You need to take a step back, reassess.
Exactly. And in this case, the model, it goes back, reviews its steps, realizes the mistake, and then corrects itself, ultimately arriving at the correct answer, which is 2.
So just adding that weight was enough to guide it back on track? That's pretty fascinating.
It is.
Does this suggest that these pre-trained models already possess a lot more reasoning capability than we might give them credit for?
I think it's a strong indication of that, yeah, sometimes they just need that little nudge in the right direction, a little more time to let those internal processes work things out.
Okay, so we've seen how budget forcing works in practice. Yeah. But you mentioned earlier that the paper also explores these parallel scaling methods. Can you tell me a bit more about those?
Sure. So they look at 2 main approaches, majority voting and tree search, specifically a method called Rebase with majority voting. You essentially run the model multiple times each time with a slightly different random seed, and then you just pick the answer that appears most often.
So it's kind of like crowdsourcing the answer from multiple versions of the model.
Yeah, that's a good way to put it. And it's a surprisingly simple concept, but quite effective. And then there's Rebase, which is a bit more sophisticated. It uses a reward model to guide a tree search, evaluating different possible reasoning paths, and then selecting the one that leads to the best outcome.
So Rebase is more about strategically exploring different options rather than just taking a vote.
Exactly. And in their experiments, Rebase actually scales better than majority voting, at least in terms of performance gains.
Okay, interesting. Does that mean Rebase is the superior approach then?
Well, not necessarily. While it shows some really promising results, Rebase also requires those extra computational resources because of that reward model. And importantly, both parallel methods ultimately kind of hit the same wall. Right. The limitations of the model's context window. You can only scale up the computation so much before you run out of working memory, so to speak.
Right. It's like trying to cram too much information into your brain at once. There's a limit to how much you can process effectively.
Exactly. And it really highlights this key takeaway from the paper that while these scaling methods, both sequential and parallel, can push performance further, they don't fundamentally change the model's underlying capacity.
Okay, so we've got these different scaling methods, but they all have their limits. What about those ablations they conducted? What insights did they gain from those experiments?
Yeah, they really did. They meticulously tested the importance of each step in their process, from the dataset creation to the specific scaling methods they were using.
So first up the dataset, they had those 3 principles, right? Quality, difficulty, and diversity. What happened when they messed with those?
Performance took a nosedive, basically. They tried a bunch of things. Creating a data set with 1,000 random samples, one focusing only on diversity, and another using the 1,000 examples with the longest reasoning traces. None of them came close to their carefully crafted S1K data set.
So it really highlights how much thought went into their approach. It wasn't just, grabbing any old questions. It was about curating a data set specifically designed to challenge and improve those reasoning abilities.
Exactly. It underscores that data quality and selection are critical, especially when you're working with a limited sample size.
Okay, makes sense. Now, what about the test time scaling methods themselves? They compared budget forcing to a bunch of alternatives. How did it stack up?
They really put it through the ringer. They tested it against token conditional control, step conditional control, class conditional control, even rejection sampling and budget forcing consistently came out on top, particularly when it came to control and scaling.
I'm curious about this rejection sampling thing. How does that even work?
It's like, imagine you're asking the model to just keep generating responses until it finds one that fits within a really strict token limit. It's kind of a brute force approach, and surprisingly, they found that it actually led to an inverse scaling trend.
So the longer they allowed the model to think, the worse it performed.
Yeah, basically it's counterintuitive, right?
But Lord, any idea why that might be?
They think it's because those shorter generations are just more likely to be on the right track from the start, while those longer ones tend to get bogged down in all that backtracking and self-doubt, almost as if forcing the model to think too much can lead it astray.
Wow, that's really fascinating. It kind of challenges our assumptions about the relationship between thinking time and performance.
Yeah, it does. And I think it just speaks to the importance of understanding the nuances of these large language model. Sometimes less is more.
Okay, so budget forcing wins this round. But the paper also acknowledges its limitations. Can you walk me through those?
Sure. So one obvious constraint is the context window of the language model itself, right? You can only extend that thinking process so far before hitting that wall.
Yeah, you eventually hit those limits of the hardware.
Exactly. It's like trying to run a complex program on a computer with very limited RAM.
Right. Are there any other limitations they highlighted?
Well, they also found that those performance gains from budget forcing eventually kind of plateaus.
Yeah.
You can't just keep adding weight prompts and expect, unlimited improvement. There's a point of diminishing returns.
So the powerful technique, but not a magic bullet.
Exactly. But I think what's really exciting is that this paper kind of opens up a whole new avenue for research. It suggests that we can achieve these significant performance gains by strategically controlling the model's computation at test time.
So instead of just focusing on making models bigger, we can explore ways to make them think smarter.
Precisely. And I think the possibilities are just vast. They hint at modifications to budget forcing itself, like using different prompts or combining it with other techniques. And they even suggest exploring its application to other tasks beyond reasoning, like creative writing or code generation.
It's amazing to think that this seemingly simple idea of controlling a model's thinking time could have these far-reaching implications for how we approach AI development and performance optimization.
I think it's a real paradigm shift, and I'm really eager to see where this line of research leads.
Well, that's our deep dive into S1, simple test time scaling. Thanks for joining us, everyone, and we'll see you next time on AI Paper Podcasts.